Hi, I'd like to welcome you to a discussion about error and uncertainty and precision and accuracy. These are things which are pretty important in science but easily misunderstood. So in physics, I definitely want to make sure you have a good understanding of these. Most people think of mistakes as an error, and I would agree that in labs or data collection we can have mistakes, and that's what this is. So it is a mistake. You might not always recognize an error as an error. Um, I think it's important when we talk about errors in lab or in simulations, we need to think about the fact that they should be fairly specific. In other words, if someone says, well, what kind of error did you have in this lab? Human error. What does that even mean? If you could say, the person didn't measure right, again, not specific enough. If you could say something more specific, such as the person measured using a different part of a meter stick than they were supposed to, or they used the inches side of a meter stick, and I'm trying to find one here with that. The inches side of a meter stick instead of the meters and centimeters side of a meter stick, then that would be an error. That would be a mistake. So we want to be specific enough to know what's going on. So please don't ever just say student error or measuring error. Not good enough. What about uncertainty? That might be something you haven't heard of very much before. And let me give an example of an activity I often do in class. So if you look here, I've got this. It's a stick, it's a dowel rod, and I would ask you to say estimate its length. And if you didn't know better, you might say 3 or 4 feet. You might say a meter, 1.2 meters, something like that. If you didn't have any sort of measuring tools. Usually I do this with the width of our desks. And then I say, well, now use whatever measuring tools you have and measure the width of it. And each group would measure their desks, and they'd get different numbers. So one might say something like, actually I'm going to pull this down. This is a 2-meter long measuring stick. If I recall, it's somewhere around 140. So this is around 136 centimeters. So we might get a group that says something like we might say something like the width of the table is 136 centimeters. We might get another group that says 1.375 meters. We might get another group that says 54 inches. We might get another group that measures really closely, and they might say something like 1.3805 meters. The difference in units doesn't bother me too much, although I would prefer to have things in metric units because that's what the world uses. Even in America, in science, that's what the world uses. If you need to work on your car, you need a set of metric wrenches, for example. So the question is why aren't these exactly the same? And there's a couple of reasons why they might not be the same. One of which is a type of uncertainty. First of all, I think we need to be careful about writing numbers down that are more precise than you can really measure. At your home or in class, the best we can normally do is about 1/10 of a centimeter as an estimate. And every measurement has an estimate as its last digit. So for example, if I measured somewhere here between, say, 62 and 63 centimeters, it's better for me to say 62.4 centimeters instead of just 62. It lets people know that I measured more precisely than just eyeballing it and saying 62. But that last digit is an estimate. And that's normal, and that's fine. It doesn't matter if it's a little bit off. Could be 62.3, could be 62.4, could be 62.5, but it's somewhere in that range and not just 62 or 63 centimeters. So even with these, we can have measurement uncertainty. So I'm going to get rid of the 54 inches there. So one type of uncertainty, again, is measurement uncertainty. This can be reduced by using better measurement tools, but it actually can't be eliminated. Students, and a lot of times I've heard teachers say that if we only had the best measuring tools, we wouldn't have any uncertainty at all. And that's not true. There are fundamental laws of quantum physics that say when you measure something super tiny and very, very finely, what's going to end up happening is that you cannot know exactly where an object is or how big it is or how fast it's moving. So quantum physics actually says there's a limit to how certain we can be. It's very small, but there's a limit. The other thing is uncertainty of event. So let me give you an example about that. Again, in class, a lot of times what I'll end up doing is I'll have students get one of these large whiteboards. They'll angle it on a desk. And let's say they've got it up here. This is a little bit off screen, so you can't see the top of it. But that's okay. And I'll ask the people to crumple up a piece of paper. Actually, I'll put it on top of it. Here. Wow, I am having trouble with this today. I think we'll get a couple books. And what I'll do is I'll have it angled, crumple up a piece of paper into a ball. And I'm going to say I want them to predict how far it rolls off the end of the ramp. So if they say something like this, well, that just is sliding and not rolling. So I'll make it a little steeper so you can see. And they might crumple it again, put it here, and they'll collect a few different measurements. Hopefully they're keeping it controlled. So we want to control variables as best we can. But it rolls to different lengths, and they'd collect a bunch of trials, and I'd ask them to make a prediction. And usually what they'll do is they'll take all these distances, they'll add them up, and they'll divide by the number of trials, and they'll get a prediction. And almost certainly it's wrong. So there's not just uncertainty of measurement, but there's also uncertainty of event. So the paper ball is so uncertain in terms of its shape that when I roll it off the ramp, it might slide, it might roll. It's not great to be able to predict that. So oftentimes when we're making predictions in science or when we get results to make predictions, we might want to give things in a range. So instead of saying my prediction is that this ball will roll and it'll end up being 37.2 centimeters off the end of the ramp, because that's what my data gave me when I added the numbers up and divided by the number of trials, maybe I should look and say, hey, the smallest I had was 25 centimeters, and the biggest distance I had was 50 centimeters. So maybe my range should be between 25 and 50 centimeters. Or maybe I could say I'm pretty darn sure it should be between 30 and 40 centimeters. I'm not getting into the statistics of an exact reason why you might choose one range or another. When you're making predictions, you want to decide on a range from all your data. You're pretty darn sure your prediction would fall within that range. If there's an outlier, we don't just get rid of it, but we want to think about why that might be. So uncertainty is not a mistake. You did not make mistakes measuring things. You may not have had the best measuring tools, but it's not a mistake. And what events you're measuring may not always be perfectly consistent. So oftentimes when we want to make predictions, we would give a range as opposed to a predicted value. So with that, I'm going to finish up. By talking about accuracy and precision. This one I think a lot of people understand. This one I've seen talked about incorrectly quite a bit. So accuracy is, we would generally think about as how close you are compared to an accepted value. So if people have done things enough, have an idea to make a very accurate prediction, and what you get is different from that, it says you would have low accuracy. An example of thinking about things is an arrow. I've seen this example before. Your goal with an arrow is to hit the bullseye, the middle of the target. So if you have something that if you fire 4 arrows, and 1 hits here, 2 hits here, 3 hits here, 4 hits here. If that's your goal, to get to the center of the bullseye, 1 is pretty accurate. 2, 3, and 4 are close to each other, but they are not very accurate. Okay? So oftentimes when we determine this, or when we talk about accuracy, we'll use an error calculation. And what that would be, actually I'm going to do that, observed value. And I'm going to move this over so we can see this a little more. Minus our accepted value, parentheses around that, all over our accepted value, put another parentheses around all that, and multiply by 100. And that would get us our percent error. So for example, if I have a predicted value, or if I have a measured value of, say, I don't know, 105 meters, and we had something which our accepted value was 50 meters, this is going to be a lot of error. Then I would do the calculation like this. I'd say observed, 105 meters, minus accepted, 50 meters. All that over 50 meters. 105 minus 50 is 55, divided by 50. So that's actually 110% error. So believe it or not, you can have more than 100% error. Hopefully we don't very often in here, but you can. The same way, some teachers talk about not having negative percent error, but if I had something like this where 105 was my accepted value, and 50 meters was my observed value, now, say 50 minus 105 over 105 times 100%. So when I do that, I get negative 55 over 105. Notice that's not going to be the same number as when I had it set up the other way. So that's going to be a negative 52% error. It doesn't really matter to me that much whether you leave this negative in here, but something that's nice about it is if you leave the negative in, it tells you that your observed value was too low. And that's useful information sometimes, because it can make you think of, well, what made my value too low? So we're going to finish off with talking about precision. Precision, in terms of how I would like to think about it, is how finely you can measure. Some people will think about precision like this. They'll say that it's when things are bunched together. Yeah, maybe, but I would like to think about it like this. So if you have a measuring tool, your measuring tool has a certain level of precision to it. So let's say, for example, I want to measure something like the width or the height of this book. What I've got here, so I've got a meter stick. It's 1 meter long. And if I use this side of it, I could only estimate that maybe it's around, I don't know, 35 centimeters long, 40 centimeters long, something like that, because there's no markings. If I turn to this side, there's markings every tenth of a meter, every decimeter. So now if I look at that, I could say, oh, it's close to the 3 value, so it's about 0.3 meters. I would estimate that's around 0.2 8 meters or so. Now, if I go to a more precise side, I can look at it again and I can say, oh, that's between 28 and 29 centimeters. I'm going to estimate 28.5 centimeters. And now finally I can go to the most precise side where I've got millimeters marked. And I could say, well, looking at this now, I'm going to have to get a really good measurement. I could say, that looks like it's 28.45 centimeters long. I don't know if we get that specific or not, but the idea is the tool you use affects the precision with which you can measure. And that's the important takeaways from today. So we've got accuracy and precision, we've got error and uncertainty. And those are things we'll be using all year long. So hopefully that helps. Oh, and make sure to hit that subscribe button and click the bell to get notifications.